Good morning, welcome. Today we're going to be starting chapter 28, the sun. It's a pretty hot topic. Yay! But before we get into that, we do need to have prayer. So let us lift our hearts to the Lord. Let us quieten our minds and hearts, and let's have a Hail Mary. In the name of the Father, Son, Holy Spirit, amen. Hail Mary, full of grace, the Lord is with thee. Blessed art thou amongst women, and blessed is the fruit of thy womb, Jesus. Holy Mary, Mother of God, pray for us sinners, now and at the hour of our death. Amen. In the name of the Father, Son, Holy Spirit. Very good. Today we're starting chapter 28, the sun. If you were looking at how large is the sun, it is that big burning ball of gas 93 million miles away. Here is a portion of the sun, and here would be the relative size of the planets accordingly. Whoa. Pluto. I've often heard it said that it would take 1.3 million Earths to fill up the sun. That's a lot of Earths. What kinds of elements make up stars? Now, we know that our star is an average star of average age and size. About 90% of our star, the sun, is made of hydrogen, about 8% is made of helium, and 2% made of all other elements. Keep in mind that all elements on the sun are on the earth, but in different abundance. All right. So our objectives in this first section, we're going to be talking about how the sun converts matter into energy. Now, it's going to be that really famous guy, Albert Einstein, who said E equals mc squared. Keep that equation in the back of your minds because we're going to be explaining that today. We're going to be talking about the radiative and convective zones of the sun, BT dubs. They get their names for how energy is moving. The radiative zone, energy is moving by radiation and waves. The convective zone is convection, where heated less dense is rising and cooler more dense is sinking. We'll talk about the three layers of the sun's atmosphere. The surface of the sun is actually the photosphere, and the color sphere is the chromosphere, and then the outermost layer of the atmosphere is the corona or crown. Here we go with the sun. All known elements are found on the sun, but about 90% of the sun is made of hydrogen, about 8% of the sun is made of helium. Let's talk about that. The major regions of the sun, and this probably sounds like it's going to be an essay question, the internal portion of the sun is called the core. The core is the hottest part of the sun, reaching temperatures of about 15 million degrees Celsius. To you and me, that's 27 million degrees Fahrenheit. I know, it's PDH, pretty darn hot. Obviously, the core of the sun is made of an extremely dense gas. There are no solids, there are no liquids on the sun. It's simply too hot for those to exist. The gravity in the core is about 300,000 times that of Earth, meaning there's 300,000 times more gravity in the center of the sun, meaning your weight is multiplied by 300,000 if you wanted to know how heavy you would be, meaning you would be so darn heavy that you would be about this tall, because if you were so heavy, your body would just compress on itself. The intense heat and pressure changes the structure of atoms. Okay, now we've learned this before. We all know that when it's so hot, atoms are stripped of their outer layer. Well, what makes up the outer layer of an atom? Electrons. Remember that the nucleus of an atom is made of protons and neutrons, and surrounding this nucleus, moving at very high rates of speed, are electrons. It's so darn hot that on the sun, these electrons that surround the nucleus have been stripped off. Well, they actually do something. They move, they separate, they go away, and they make up what we call the solar wind. We'll learn more about that. The electrons are stripped off the atoms, leaving their nuclei exposed. Well, I don't know about you, but when I get hot, I start taking off layers until it's illegal to take off anymore. Well, with these exposed nuclei, they're going to fuse together. And when they fuse together, they make not only a larger nuclei, but they make different elements. Now this is where Albert Einstein came in and said, when hydrogen and hydrogen fuse together, they form a nucleus of something called helium. When they fuse together to form helium, they give off energy in the form of light. It's this light that makes the sun the sun. The nuclei join with other nuclei, forming even larger nuclei. And this is how the sun gives off light. It's this fusion. It's this fusion, this coming together of nuclei that produce the energy of the sun. We call it hydrogen fusion. Why is it called hydrogen fusion? Because hydrogen is fusing. If it would have been iron fusing with iron, it'd be called iron fusion. Or if it were carbon fusing with carbon, it'd be carbon fusion. Well, hydrogen fusion is hydrogen fusing with hydrogen. H plus H yields He, which is helium, plus light. That is hydrogen fusion at its best. Every second, 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi. Every second, 600 million tons, 600,000 tons, 600 million tons, this quarantine thing. Every second, 600 million tons of hydrogen are changed to helium. That's a lot. Eventually, the amount of hydrogen will be increasing, but the amount of helium will be decreasing because you're changing. Good gosh, I'm having trouble today. Eventually, the amount of hydrogen will run out and helium will increase. Energy is then given off in the form of light. Here is hydrogen fusion at its best, where hydrogen and hydrogen come together to form helium, and they give off energy in the form of light, and they make a helium nucleus. That's awesome! That is awesome! In 1905, Albert Einstein came up with this theory that E equals mc squared, where E represents energy. He was trying to explain how so much energy can be given off by such a small amount of matter, where E equals energy, M is the mass, which is a small amount, and C, which is the speed of light, which is like, 300,000 kilometers per second, or 186,000 miles per second squared. But he explained how such a small amount of matter, hydrogen is the smallest atom on the periodic table, how two of these small hydrogen can form helium and give off energy in the form of light. How so little matter can produce such a great amount of energy. Albert Einstein. Right here. All right, so you have the core. Surrounding the core, you have these two things called inner zones. The first of which is called the radiative zone. The radiative zone gets its name because energy in the radiative zone is moving by radiation, which is energy moving in waves. It has a temperature of about 2.5 million degrees Celsius, or to you and me, that's 4.5 million degrees Fahrenheit. Still pretty hot. But it's a lot cooler than 27 million degrees Fahrenheit in the core. Energy moves by radiation, which obviously is just energy moving in waves. This is how this zone gets its name. The convective zone surrounds the radiative zone. The convective zone gets its name because energy is moving by convection. Heated, less dense materials rising, cooler, more dense materials sinking, and this rising and sinking moves energy, and it creates this rolling motion. Remember the asthenosphere? Just saying. Energy moves by convection. This layer is cooler at 2 million degrees Fahrenheit. Still pretty hot. Surrounding these inner zones, you have what we call the atmosphere. And there are 3 layers of the atmosphere. The atmosphere. The photosphere is considered the sun's surface. I don't know if you remember in biology when we talked about photosynthesis, we said photo means light and synthesis means putting together, and it was how organisms containing chlorophyll were able to put together, using light, put together molecules using light, and they made food, right? Okay, well, the word light, photo means light. Well, the photosphere is where the light is coming from. And when we look at the sun, we're actually seeing the photosphere. I probably shouldn't say when we're looking at the sun because we shouldn't look at the sun directly. If we do, we should be wearing protective gear. Remember the eclipse a couple of years ago? And all the school kids went outside wearing those cardboard eclipse glasses? That's one way you can do it. The photosphere is made of these gases. To me, this looks like a pot of boiling macaroni noodles. And these macaroni noodles are boiling because the heated, less dense water is rising, and then the cooler is sinking, creating this bubbling motion. The photosphere has a temperature of about 6,000 degrees Celsius. To you and me, that's about 11,000 degrees Fahrenheit. This is the coolest layer of the sun. It has a grainy appearance because of these gases that are rising and falling, creating this bubbling appearance. This is the photosphere. It has what we call a granulation effect. This is where visible light is given off. Remember visible light, Roy G. Biv, the red, orange, yellow, green, blue, indigo, violet? Surrounding the photosphere is the color sphere, aka the chromosphere. The prefix chromo on the word chromosphere means color. This is the part of the sun that glows with like a reddish glow. It has a temperature of about 50,000 degrees Fahrenheit. Wait a minute! You mean we went from the core being the hottest, and then we went radiative zone a little bit cooler, convective a little bit cooler, photosphere the coolest, and now we're going out from there, we're getting hotter? Yep. And we're going to get even hotter in the corona. Just wait. Gases can make hot jets of gas from this layer. We're going to talk about these in the next section. And then, of course, you have the word corona. The word corona is a word that means crown. And I'll bet anything when, you were in grade school and you used to sit down and draw pictures in art class, and you drew a house and a tree and a bird, and you drew the sun in the upper corner. You drew like a ball or a portion of a ball, and then you made like these things coming out from the sun, like streamers coming out, or maybe you just kind of went like this. That was the corona. You were drawing the corona and you probably didn't even know it. The corona is even warmer than the chromosphere. It blends outward into space. It has a temperature of about 2.7 million degrees Fahrenheit. That's so weird how you went from hot, cooler, cooler, coolest, warmer, warmer? That's wild. I know, that's the sun. The ions escape out from this corona. They produce what we call the solar wind, and that solar wind is what travels through the universe. We'll talk about the solar wind when we talk about auroras. I've gone ahead and I've put a series of slides on here that you can watch to identify the different layers. Let's talk about solar activity. Section 2, solar activity. We're going to talk about sunspots and what sunspots are and how they respond to powerful magnetic fields. Now, I know this is section 2. I'm just going to go ahead and do the whole PowerPoint for the whole chapter in one. It takes so long to upload videos. Let's just go ahead and do the whole chapter. We're going to talk about prominences in solar flares. We'll talk about a solar wind, how they can create auroras here on Earth. Here we go with solar activity. Two things create solar activity. Number 1, convection currents. Heated, less dense materials rising, cooler, more dense materials sinking. And number 2, the sun rotating on its axis, spinning on its axis. Did you know that it takes the sun 25.3 days to make one complete turn? But that's at the equator, because the poles, north and south, take 33 days. Wait a minute. Why does the sun spin at different rates? Why are the poles spinning slower than the equator? Why is the equator spinning faster than the poles? Remember, the sun is a gas. It's not a solid entity. It is a gaseous body. And as this thing spins, it spins at different rates. Now, we're going to find out that scientists found out that the sun rotates at different speeds by studying something called sunspots. Sunspots. I have a spot here. It's not coming off. That's not coming off. No. Sunspots are not spots like, you get a spot on your glasses or on your windshield or something. A sunspot is an indication that there's a cooler area there that exists on the surface. What's the surface again? The photosphere. There's a cooler area within that photosphere. Well, what causes that cooler area? At my house, we have an electric range, and when you turn the burners on, it's a flat glass top. And when you turn the burners on, they go from black and they glow to a reddish color. And then when you turn the heat down, it goes from red back down to black. And that color shows you that if it's red, don't touch it, it's hot. If it's black, it's got to be a little cooler. Well, that's a great way to explain this whole sunspot thing. These sunspots are cooler areas, and they're caused because not as much heat has risen here. Well, what causes less heat to rise? Well, we're going to find out that less heat rises when magnetic fields pull on those convection currents. What am I saying exactly? Well, convection currents are when heated less dense materials rise. If you could somehow slow the rising of the heat, slow it down so less heat rises, you're going to get a cooler spot. And that's exactly what a sunspot is. Powerful magnetic fields are slowing down convection. When convection is slowed, not as much heat rises. With not as much heat rising, a cooler spot forms. The cooler spot is called a sunspot. Ta-da! Did you know that these sunspots can be up to 3,000 degrees Celsius cooler? So, trick question. You could answer in one of two ways. Where is it the coolest on the sun? Well, you could say the surface, the photosphere. Okay, the photosphere is the coolest. You could be a real smarty pants and say a sunspot on the photosphere. See what I mean? Sunspots can occur anywhere on the surface of the sun, but as scientists were watching in the sun and taking, drawings of the sun, they found that sunspots went from the South Pole up towards the equator, or they moved from the North Pole down to the equator. And they thought, well, that's kind of strange. Why would they move from here up or from here down? Because the equator is spinning faster than the poles. It takes the poles 33 days to make one turn, but it takes the equator only 25.3 days to turn. That's crazy. I know. But that was what indicated to scientists that, hey, the sun is rotating, and it is rotating on an axis, a point that sits, and this ball rotates on it. Now remember, this ball is not a solid. The sun is a gas. The sun is a gas. No, wait. Let me start over. The sun is a mass of incandescent gas, a gigantic nuclear furnace. Okay, well, I gotta stop now. But I'm sure Shelby Wesselman is singing with me right now. Every 11 years, there are more sunspots than normal. We call that a cycle. The sun has an 11-year sunspot cycle. There are always sunspots, but every 11 years, more than normal. The last cycle was in the year 2010, so guess what, you juniors? When you graduate, 2021, we will be in a sunspot cycle. Cool. Solar disturbances. I want to talk to you about prominences and solar flares. Prominences and solar flares are pretty similar, but a solar flare is a hot jet of escaping ions, like whoosh, outward like a Roman candle, whereas a prominence is an arch. It's like two solar flares that have arced together. A prominence is an arch of escaping ions, forming a curved path, kind of like the handle on a coffee mug, an arch. Whereas a solar flare, oh, there's your comment, sorry about that. A solar flare is a sudden eruption that comes straight outward. Now remember, you can go back and watch this video, but this this PowerPoint is posted on Schoology. You don't have to listen to my voice. You don't have to look at my face. You can just watch the PowerPoint posted on Schoology. The particles of these solar flares create the solar wind. Sometimes the solar wind is so incredibly powerful that it can disrupt our communication satellites. When those communication satellites are disrupted, that means that anything we rely on, whether that's television or radio or even cell phone communication, can be interfered with. Maybe we get static, maybe we get dropped calls, maybe something really hooey-fluey happens because these ions that are escaping the sun approach the Earth and they can knock our satellites out of reach. They can disrupt what we call the Earth's ionosphere. The Earth's ionosphere is the part of the thermosphere where we, beam our signals to and receive transmission from the ionosphere. It can disrupt our magnetosphere, causing magnetic storms. Now, scientists have been working on a way to harness the energy of those magnetic storms, kind of like they did in Monsters, Inc., when they tried to harness the power of kids' screams, and then they found out that kids' laughter had more power than screams. So they are looking at ways to harness this energy, to use it as an alternate energy source here on Earth. Solar flares. Here you can see one happening. Auroras. Now, an aurora is an effect seen here on Earth, not on the sun, but it is due to the sun's activity. An aurora is a band of these brilliant light shows, if you will, caused from those solar particles hitting the gas molecules in the Earth's atmosphere. And when those gas molecules are hit, they create these wonderful sheets of light. Now, normally these auroras are going to be seen more towards the north and south poles because that's where the Earth's magnetic field is the strongest. That's where the force is the strongest pulling these particles in. The particles strike the gas molecules in the atmosphere and they do produce the greens, the reds, the blue, the violet sheets of light. And they're going to be more common in the fall and spring when the hours of daylight and night are about the same. The auroras at the North Pole are called Aurora Borealis. The auroras at the South Pole are called the Aurora Australis. Not in your textbook, but I thought, for those of you who are in trivia nights, maybe you want the information. So you can go through the different layers of the sun. Let's finish up with the formation of the solar system. So how old is the solar system? Okay, take a deep breath. We say that the universe is about 17 billion years old. That's when that sphere of all the gas and energy in the entire universe exploded and stuff was sent outward and particles coalesced and collided and combined and blah, blah, blah. And the galaxies formed and the solar systems within there formed and blah, 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 blah. Okay, fine. We say that the Earth is a planet in a solar system. A solar system is defined as a system of planets that orbit a star. Our star obviously is the sun. We say that our sun and the Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, and all the other moons and asteroids that orbit the sun is about 4 to 5 billion years old. So let's talk about the formation of our solar system. The sun and the planets developed at the same time, about 4 to 5 billion years ago, out of a huge spinning cloud of gas and dust called a nebula. Now, all solar systems formed out of a nebula. A nebula is a cloud. It's a cloud of gas. It's a cloud of dust. It's a cloud of energy. And particles are going to collide, and they're going to combine, and they're going to coalesce. Shock waves from a nearby supernova cause this nebula to contract, condense. Well, particles started to contract and condense. The objectives in this section, we're going to talk about that nebular theory. We're going to talk about how our planets develop. We're going to talk about our land, our atmosphere, and our oceans of water here on Earth. Why is the Earth unique in the solar system? Well, we have an atmosphere with enough breathable oxygen to sustain life. We have water found in liquid form, and we have life. Earth is like the Cinderella planet in the solar system. So here we go. The planets and the sun. So you've got this big, huge nebula, and the center is where, is spinning the fastest. The greatest amount of energy is right here. Guess where the sun forms? That's right, right there. And then here's what's happening. The planets are starting to form, and you can see like a planet starting to form here, a planet is kind of forming here, a planet is forming here. So they took one out and they said, here's Earth. Now, I don't know about you, but I don't see oceans, I don't see trees, I don't see dinosaurs, I don't see people. Because as the Earth was forming, particles are colliding, particles are condensing, meteors are hitting and bombarding the Earth. The Earth was a molten mass. A molten mass with no shape, no form, right? And this molten mass is spinning on its axis, so it's going to take on a rounded formation. Interesting. Now, eventually the Earth starts to cool down and it starts to degas. It's kind of like when you take a cake out of the oven. You've made the batter, you've poured it in the pan, you've put it in the oven, you're taking it out in 25, 30 minutes, and the cake might be kind of tall, and then after the cake cools, it kind of degases and kind of shrinks down a bit. That's exactly what happened to Earth. We're going to talk about how these particles called planetesimals kind of collided and combined and stuck together and formed these bigger things called protoplanets, and these protoplanets condensed. As the Earth cooled, we developed our layers. So here we go. How old is the sun? Well, between 4 and 5 billion years old. Well then, how old is Earth? Well, between 4 and 5 billion years old. Well, then how old is, I don't know, Jupiter? Well, about 4 to 5 billion years old. Well, what about some of those asteroids that are in the asteroid belt between, Mars and Jupiter? Well, about 4 to 5 billion years old. Because the sun and the planets formed at relatively the same time. Anywhere between 4 and 5 billion years ago, that cloud of gas and dust called the nebula started to condense. Heat from collisions. Now listen up, this is a question on tonight's homework. Heat from collisions and pressure from gravity caused that cloud to become hotter and more dense. As it became hotter and more dense, particles started losing their outer electrons, leaving their nuclei exposed. Nuclei started fusing together. When the nuclei fused together, they formed, larger nuclei, but gave off energy in the form of light. This is why the sun gives off light. Right here. Right here. About 97% of our solar nebula form the sun. Now, what happened to the other 1%, you ask? Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, their moons, the asteroids, the comets and meteors. That's right, I said it. Everything else in our solar system, including all the planets and their moons and all the space rock and junk, make up the other 1%. Sun's huge. Huge, I tell you, huge. Well, at the same time the sun was forming, so were the planets. Some planetesimals, what's a planetesimal? A planetesimal is like a small chunk of stuff. What kind of stuff? Well, it's got hydrogen and helium and lithium and beryllium and carbon and nitrogen and oxygen and sulfur and iron and all the elements. A small junk of stuff joined through collisions and gravity, forming protoplanets. Some of the protoplanets condensed into moons, some form planets. What's the difference between a moon and a planet? A planet orbits the sun. A moon orbits a planet which orbits the sun. Well, okay, so is this how the Earth's moon formed? Commonly accepted theory, no. The Earth's didn't form this way, the Earth's moon. The Earth's moon was actually part of Earth. We'll get into that. Planets and moons are smaller and more dense than their original protoplanets because remember they had to degas like the cake that came out of the oven. So, have you ever thought about Mercury, Venus, Earth, and Mars being like heavy, dense, rocky planets? But then when you think of Jupiter, Saturn, Uranus, and Neptune, you think of them as being huge gas planets? Great way to think of it, because the distance between the forming planet and the sun determine the planet's composition. And by that I mean these planets closer to the sun are heavy, dense planets. I didn't say that they were huge. I didn't say that they were small. I said that they were heavy and dense. These are your rocky planets. Your Mercury, your Venus, your Earth, and your Mars. These are rocky, dense planets. Jupiter, Saturn, Uranus, and Neptune. Those are great, big, gassy giants. What about Pluto? Okay, I'm going with Pluto as a planet. Neil deGrasse Tyson says it's a planet. I like Neil deGrasse Tyson. I'm going with it as a planet. But it most likely was a moon of one of these outer planets, most likely Neptune, and something hit it, like, I don't know, another space rock, knocking it out of orbit, but yet it had enough speed to escape Neptune's orbit and then took on its own orbit around the sun. That's why we call Pluto a planet. The inner planets contain heavier elements such as iron, but maybe they were big. Maybe Mercury was the size of Jupiter at one time, but because of its proximity to the sun, the heat from the sun burned off Mercury's very thick atmosphere. Maybe, like I said, Mercury was this size at one time, but because it was so close to the sun, the heat robbed it. The inner planets are called inner planets because they're inside an asteroid belt. If I were dividing these planets from these, I would put the asteroid belt there, with the inner planets being inside the asteroid belt and the outer planets being on the other side of the asteroid belt. Jovian, meaning similar to Jupiter, these formed outside the asteroid belt in colder parts of the nebula. They're huge. They do have rocky cores, however, but they're extremely huge planets. They don't have a lot of gravity because they're so huge. And, all right, formation of the Earth, finishing up. When the Earth was first forming, it was amorphous, meaning it didn't really have shape or form. It was a ball of liquid goo. And this liquid goo was hot, right? Well, the Earth was very hot when it was first forming. 3 reasons. Reason number 1, why was it so hot? Because it retained a lot of heat. As those planetesimals were colliding with other planetesimals, ow, that's hot. It retained a lot of that heat. Number 2, the outer layers compressing on the inner layers caused it to retain a lot of heat. It's like when you're in bed, if you had 15 blankets on top of you, you're going to be a lot warmer than if you just had a sheet on top of you. And number 3, radioactive materials. Radioactive materials losing their neutrons, becoming more and more unstable, releasing heat. Well, because this amorphous Earth was so hot, it pulled heavy, dense materials towards its center, towards its core. Where is the greatest amount of iron on Earth found? In its core. You can still find iron on its surface, right? I mean, we're still mining iron. You can mine iron. You can find iron. But the greatest majority of the iron is making its way towards the core, and it's still making its way today towards the core. The Earth eventually cooled and divided into three main layers. The thinnest where we live is, of course, the crust. Oh, I forgot the order I put these in. I'm sorry. The center is called the core. That's where your greatest amounts of iron and nickel, very heavy, dense materials are found. And then the mantle, which is a solid rock. And then the crust, which is the least dense material where we live. We have an atmosphere. All planets have hydrogen and helium gases in the atmosphere. All planets do. But the Earth has enough oxygen in its atmosphere to sustain life. A couple chapters ago, we learned that the Earth's atmosphere is like 78% nitrogen, 21% oxygen, 1% argon, helium, carbon dioxide, etc., etc., etc. The atmosphere grew from collisions and gravity. The hydrogen and helium was captured from that nebula. Carbon dioxide was then absorbed by the ocean waters. Did you know that when it rained for 40 million years, filling in all the low-lying areas, forming your lakes, rivers, streams, and oceans, did you know that that water wasn't blue? It was actually green? And mainly it was because we weren't able to recycle oxygen at that time. There was so much carbon dioxide in the atmosphere, and we didn't have plants, folks. We only had like one-celled archaeobacteria, and that archaeobacteria wasn't able to photosynthesize until it became cyanobacteria. Look it up; it's pretty interesting stuff. Photosynthesis from that cyanobacteria increased the recycling of gases. Once that cyanobacteria was able to make oxygen, then the water started turning blue. Look it up; it's a pretty interesting fact. Some of the oxygen turned into ozone, chemical formula O3. Remember, ozone is that stuff, that gas, that very important gas that blocks us from harmful ultraviolet radiation. Found in every layer of the atmosphere, but found in greatest amounts in the stratosphere. Then the Earth cooled enough for water to fall, and it rained for 40 million years. Give or take a day. So funny. So we've had an atmosphere similar to today's atmosphere for about 1.5 billion years. So for 3 billion years, we didn't have an atmosphere with breathable oxygen. Interesting. All right. So I know I gave you all 3 sections of the chapter in one dose. You don't have to sit and watch all 3 sections at the same time. Block it off into sections, make it easier to digest. I know I'm a lot. So, can't wait to see you soon. Take care.